Okay, recording has started. All right, good morning, everybody. So welcome back to Math 115. A couple of announcements before we, well, maybe not announcements, but a couple of administrative items to discuss really quickly before we start. So hopefully you can see the screen. Okay, so I have uploaded to Blackboard a skeleton of all of the notes that we're going to do for the next few days. Okay. So it's listed as like week 3 notes, parentheses, work in progress. So if you go on Blackboard, you can find all of this stuff. And if you have a tablet or if you have a printer, then you can either follow along on your tablet or print it out and follow along on paper. And keep these notes if you want. You can also use them to look ahead if you want to see what we're going to do next. So my goal is to post something similar every Monday. And that would cover like whatever we're going to do for the next Tuesday, Wednesday, Thursday, and following Monday. So that's my plan. Hopefully I can stay on top of that and keep these all up for you, because I think some students had requested that. Okay, so that's a thing. What else is a thing? I posted your homework grades to Blackboard. However, I want everyone to remember Blackboard will lie about your, I don't know, they call it like your total grade or something like that. Okay, it'll tell you exactly like how many points you've earned on all assignments across all of everything. And in Blackboard, I list the homeworks as like worth 10 points or whatever, and I would list the exams as worth 100 points and the exit slips as worth 1 point. And it'll get sort of close to the actual weights of the grades for the class, but it won't be totally accurate. Okay, so if you want to compute your grade, you need to use the weights. So you need to use the weighted system to compute your grade. And if you don't know how to do that, that's totally okay. You can either email me and we can set up an appointment to talk about your grades, or if there's like nobody else in office hours, you can just come to office hours and it'll be, you know, relatively private, and we can compute your grade. I can't give you your grade over email because FERPA. And it's just way too difficult to make Blackboard do what I want it to do. So yeah, use the weights. If you don't know how to use the weights, come and talk to me, okay? So that is that. Okay. So let me finish up really quickly what we were doing last time, which was we were talking about equations of circles. And so we sort of defined, or we showed really, why the equation of a circle can be written as x minus h squared plus y minus k squared is equal to r squared. Okay, remember that came from the Pythagorean theorem, and I drew an really awful looking horse, or sort of not horse, to demonstrate how we define what a circle is. Okay, we said it's the set of points which are r units away from a given point. And the points that are on that circle are going to satisfy this equation. Okay, so if we plug in x and h and y and k and r into this equation, we're going to get the same thing on the left-hand side as we get on the right-hand side. So the equation is going to be true. Okay, so that was an equation of a circle in standard form. And we talked about how to graph them. Okay, so we had this example where we had x plus 2 squared plus y minus 3 squared equals 25. And one kind of important thing was that we had to remember that in the formula, okay, or in the equation, h and k have a negative sign in front of them. Okay, so when we see x plus 2, that really means that h is negative 2. And when we see y minus 3, that really means that k is positive 3. Okay. Okay. So that was how we graphed that circle. We just found its center, and then we went out 5 points in all directions from there, and we graphed that circle. Okay. So the last thing that I was trying to get to that day that I didn't quite have time for was how to convert circles from general form into standard form. Okay, so let's say we see something like the following. We're given x squared plus y squared minus 6x plus 8y plus 10 is all equal to 0. Okay, and this, if I were to ask you to graph it, well, if I was to ask pretty much anybody to graph it, I think they would be really confused and not know how to graph it. And I wouldn't know how to graph this either without first converting it into the sort of standard form, I think is what we call it, right? Yeah, standard form. Okay, so the way we do that is just by grouping up all the x terms. So first step is to group x terms, group y terms, and move any regular numbers over. Okay, so after we do that, we will have, let's stick with blue. So after that, we will have x squared minus 6x plus y squared plus 8y equals negative 10. Okay. Now, does anybody have an idea of what I might try to do next in order to, fill in the gaps here and then wind up with something like x minus blank squared plus y minus blank squared equals some number? Any ideas what we could do in the intervening steps? Not quite FOIL and factor, but you're on the right track. GCF is kind of, you guys are all in the similar vein here. You're all in a similar vein. Yeah, we could rewrite a little bit. That's basically what we're gonna do, yes? Grouping. Okay, yeah, you guys are all like, it's on the tip of your tongues. Okay, so here's how we could think about it. If we wanted to really if we wanted to really be smart about things and we didn't know how to proceed, we could just write A here and B here, or why don't we even just do H? We could write H here and K here and R here. And what we could do is then FOIL this out in this direction would be x minus 2hx plus h squared, and then plus y squared minus minus 2k Yeah, but k is going to be negative again. Okay, yeah, so we can do this, minus 2k, and then 2kx, and then we'll have plus k squared equals r squared. And then we could move the h squared and the k squared over to the other side, and we'd have something like x squared minus 2hx plus y squared minus 2kx is equal to negative 10 minus h squared minus k squared. And then we can kind of see that what we want here is for this 2h to fulfill the role of this negative 6 here, right? We want minus 2h to fulfill the role of the minus 6x, and we want minus 2k to fulfill the role of positive 8y. Okay, so we're going to do a process which is called completing the square. You might have heard of completing the square. So the second step is complete the square. For the x terms and the y terms. Okay, so we're going to complete the square twice. And the way we complete the square is by doing the following. We'll do x squared minus 6x, and what we're going to do is we're going to take this number and we're going to divide it by 2 and then square it. Okay, so let me write that off to the side. 6 divided by 2 squared is going to be 3 squared, which is 9. And I'm going to add that here. Okay. Now I'll have y squared plus 8y. Now I'm going to take 8 divided by 2 and then square that. And I get 16. So I'll add 16 here. And bear with me for a second if this seems like it's not going anywhere. And then we have our equal sign. And then we have to be a little bit careful. Because what have we done? We have added, okay, we've added 9 and 16 to this side. So in order to balance out our equation, we need to do the same thing on the right-hand side that we did on the left-hand side. So all we did was add something. So I'm just going to add that back on the other side. Okay, so I get negative 10 plus 9 plus 16. Okay. And now, oh geez, got myself in trouble here. Let me erase this here. And now what we can do is we can take each of these two quadratics, okay, this first one and this second one, and we can factor them, okay? We want two numbers which are going to sum to negative 6 and multiply to 9. Well, by design, this is going to factor as x minus 3 squared plus, so okay, let me move this down and we'll say the third step is to factor. Each quadratic. So we'll get x minus 3 squared, and the second one factors as x plus 4 squared. And then the right-hand side, we just combine. Negative 10 plus 9 is going to be negative 1, plus 16 is going to be 15. So our conclusion is the circle has its center at 3, -4, and radius r equal to, what should r be? If we have x minus 3 squared plus x plus 4 squared is equal to 15, what should the radius of this circle be? You're close. Yeah, we should take the square root of the right-hand side, right? So we should just we can just leave the 15 in there. And 15, I believe, is going to be irreducible, right? Because it would factor as 3 and 5, and we only have one of each of those, so we wouldn't be able to bring anything out. Okay, great. So that's how we do this process. It's a process of grouping the x terms, then we just complete the square for each of these we treat the y's by themselves and we treat the x's by themselves. Okay, so some students find it helpful if they write these brackets here. And then we just complete the square for each set of brackets. But we need to remember to balance out whatever we do on the left-hand side, we need to also do to the right-hand side. So when we added 9 and when we added 16, we have to do that to the right-hand side as well. Okay. There we go. Okay, so that's the last thing that I had to say about circles. So before we move on to any of the new material, are there any questions about dealing with circles and equations of circles and doing this conversion between general and standard form? Okay, sounds like not. So let's move on and talk about lines. Okay, so we have lots of different equations of lines. So I'm going to go through a few right now. The first one, well, the one that everybody seems to remember well is slope-intercept. People like this one, right? That one's the familiar old y equals mx plus b, where m is the slope and b is the y-intercept. Remember, I think we talked last time about what a y-intercept is. Okay, and point slope is the one that people tend to forget. It's given a point on the line x1 comma y1 or x naught comma y naught. Sometimes people write it like that. And the slope m the equation of the line can be written in the following way. We'd write it y minus y naught is equal to m times x minus x naught. Okay? And if you take this point slope form, okay, and you were to distribute this m onto each of these terms, and then solve for y, then you're going to get slope-intercept form. Okay, so it's not so hard to convert from point-slope form into slope-intercept form. Going the other way takes a little bit more thought. Okay, and really quickly, let me remind you that m, the slope, m, is going to be the rise over the run. For example, y equals 2x, the slope is 2. That means that for every 1 unit, which I move to the right, the height of our graph will increase by 2 units. Okay, so y equals 2x, we would go over 1 and then up 2, and then over 1 and up 2. Okay, so it would look like this, where, let's see, this was 1 unit, and this was 2 units that we went up. Okay, so it's the rise over the run. Okay. Any questions about point slope and slope intercept? Are these familiar to everyone? Yes, no, maybe? Okay, familiar. Good. All right, the last one we have is general form. We probably won't deal with general form that much. You might have a problem where you're asked to convert between general form and slope intercept or something like that. Pretty much any time I see a problem where I am given the equation of a line in this way, I just roll my eyes and then I convert into slope intercept. Okay, so it looks like Amkumar wants a little bit more explanation about slope intercept. So let me dive into this a little bit more. So m here is going to be our slope, and b here is going to be our y-intercept. Okay, so if we have a slope-intercept problem, such as, say they give us y equals, I don't know, x plus 3, then the slope is the coefficient on x, which in this case is just 1, and the y-intercept is going to be equal to 3. So if we were to graph that, what that means is that the slope of the line is going to be 1. Okay, so it's going to look something like this. And the question now is, where does it cross the y-axis? Okay, where does it cross the y-axis? And it says that the y-intercept is positive 3. Okay, so if we were going to draw some lines on here, we know that the point at which our line should cross the y-axis is going to be when y is equal to 3. Okay, so we'll put a little dot there, and that's where our line should cross the y-axis. Okay, so this is how it's defined. We have a direction and a point at which we're going through. Okay, so this is really just point slope again, except the given point on the line, x naught, y naught, is the point 0, 3, for example, or 0, b. Okay, so slope intercept is just point slope where we're given the point 0, b. All right, so that is how we do that. All right, if you have more questions about point slope and slope intercept, you stay after class today for a little while and we can talk some more. Okay, so as I was saying, general form ax plus by plus c equals 0, generally just convert it directly to slope-intercept form by adding the appropriate things over to the right-hand side and dividing by the appropriate things, and just get yourself into a position where it looks more familiar. Okay, horizontal lines. They look like they're lying down flat. And that's a horizontal line. And they have the form y is equal to c, where c is a number. Okay? So if we were to graph, we would have our lines here, and then this point would be the point height c. Okay, so horizontal lines are defined by their height. Okay? If you draw a bunch of horizontal lines, it's not hard to see that the difference between them is just going to be how tall they are. Okay? Excuse me. Okay. So then vertical lines are going to be sort of defined by their x-coordinate, right? We would count how many to the left we are, and that would be the point C. And our vertical lines are going to have the form x is equal to c, where c is a number. Okay, so basically horizontal lines and vertical lines are going to be where the slope is either undefined or slope is 0. In fact, for horizontal lines, the slope is going to be equal to 0. And for vertical lines, the slope is going to be undefined. The reason that it's 0 for horizontal lines is we can count. If I move 1 unit to the right, how far up did I move? Well, I moved up 0 and over 1. That's equal to 0, right? However, if I have this vertical line and I want to count the rise over the run, well, how much did I rise? I don't know. How about 1 or 10 or 1 million? And my run was actually going to be 0. I didn't move left and right at all. So I've got 1 over 0. And we say that we don't define 1 over 0. Okay? We can't do it. Okay, so that's horizontal and vertical lines. So let's graph some lines. Okay, so this one looks like it's in slope-intercept form, not slope-intercept form. This is in point-slope form, where the point is 1, 3. Remember, this is like the circle thing where we've got a minus sign here. Okay, on our point slope, we have y minus y naught equals m times x minus x naught. So in our case, x naught, oh my gosh, x naught is taking the place of 3, and 1 is taking the place of y naught. So the point is going to be the point 3, 1, and slope is equal to 6. Okay, so let's get some digits on here. So 3, 1, that's the point right here. So we know that point is on the line, and we know that our slope is 6. So if we move 1 over to the right, we should go up 6. So move 1 over to the right and go up 1, 2, 3, 4, 5, 6. And that'll be our point for our next one. And now we're just going to draw a line which goes through those points. So that's how we would graph this line. Okay? So once you have 2 points, right, all it comes down to after that is connecting them and then kind of like extending them, right? 2 points will define a line. So what I like to do is just plot the first point, which is given to us right in the equation, and then get one more point by moving 1 over and going up by the slope according to what the slope is, and then that gives us our second point. And once I had these 2 points, all I had to do was connect them. Remember, this distance here was 1 and this distance here was 6. And that's how we would graph that line. Okay. Here's one that's in slope-intercept form. Okay, who can tell me what is the slope of this line here? It's a little bit ambiguous since we don't have a number right out front. Any ideas on what is the slope of this new line? That's right, I think Heidi and Mitchell have got it. It's going to be -1/2, right? Because we could rewrite this. -x divided by 2 is the same as doing -1/2 times x minus 1. Okay, so our slope here is -1/2, and b, our y-intercept, is -1. So the first thing to do with plotting our graph here is going to be going down to -1, recognizing we're definitely going to have a point right there. Okay, and now we just need one more point. We can get it in either of the following ways. We could try to say, okay, let's go over 1 and down by 1/2, or we could say, let's go over 2 and down by 1. Okay, so I'm going to go over 2 and down by 1, get this point. So you can kind of think of this as we went down. This is like -1 and this is 2. So if we consider our rise, over our run, we went down 1. So the rise was -1 and the run was 2. Okay. So that's what that one looks like. Okay, over 2 and down 1. All right. So, okay, here's one of those ones where they give it to us in general form just to be annoying. Remember, the strategy for this one was just to get it into slope-intercept form. So that's what I'm going to do. I'm just going to move everything that's not with a y over to the other side. So I'll have -4y is equal to -3x minus 12, and I'll divide everything by 4. And I'll get y is equal to positive 3/4 x plus 3. Okay, so now I have it in slope-intercept form. My slope is 3/4, and my y-intercept is going to be +3. So if I want to graph this, all I got to do is go up to +3. And what I want to do is go up 3 and over 4. So 1, 2, 3, 4. 1, 2, 3. Should go to this point right here. And then I should connect those. kind of like that. And remember, to get up there, my run was 4, and my rise was 3. So the rise over the run was 3 over 4. It satisfies this equation. Okay, so that's how we would graph that. Okay, are there any questions about how we graph lines? Okay. Let's see here. Make sure I hit everything in this section. Okay. So let's talk about parallel lines and perpendicular lines. Okay, so parallel lines are going to be the following. 2 lines, L1 and L2, are parallel if what property has to hold for lines to be parallel? Anybody recall this from a previous math course? We have 2 lines and we call them parallel. What property do they share? Yep. Chris and Savannah and Mitchell, they all got it. They should have the same slope, okay? So what we should do is we should draw a line like this, and you know what? I'm gonna be clever and just copy it and paste it down here. Nice, that worked out well. Okay, so this one can go anywhere, and these 2 lines are gonna be parallel, okay? So let's call this one L1, and we'll call this one L2. Why don't I put the L2 down here, though? Okay, and L2 can be anywhere up or down. Okay, you can imagine it moving up and down here, changing our y-intercept. And the property that makes these 2 lines parallel is the fact that they're going in the same direction. Okay, they're going in the same direction. So they're going to go on and on forever and never cross. Okay, so if we'll call the slope of line 1 M1, and we want that to be equal to the slope of line 2, we'll call that M2. Okay, so that's what it means for lines to be parallel. Now, perpendicular lines look somewhat different. I will do my best to draw good perpendicular lines here. Perpendicular lines kind of look like this. Okay, and they're defined by the fact that at the place where they cross, we're going to have a 90-degree angle here. Okay, a right angle. Okay, so L1 and L2 form a right angle. In other words, what property should their slopes have? Anybody know what property the slopes should satisfy? Yeah, Chris has it. They should be inverses of one another. And when we say inverses, well, okay. There's multiple notions of inverse in math, so we should be a little bit more careful than then inverse, we should say probably negative inverse. Okay, what we want is for the following property to hold. M1 times M2, we want that to be equal to -1. Usually when we say inverse of M1, we mean that M1 times M2 would be equal to 1. Okay, that's what we mean when we say, quote, multiplicative inverse. But yeah, we want it to be the negative reciprocal, like Aeon's saying here. Okay, so we want this -1 here in particular. Okay. So let me just erase this because I don't want anybody to get too confused. We want the negative reciprocal. Okay, so if this property holds, then it's going to be true. So if this slope was something like 1/3, and this slope was something like -3, then that would do the trick. All right, so that's how we form perpendicular lines. Okay, great. So now we have an example. We have some line which is defined in general form, so why don't we just start the problem by immediately solving that for a slope-intercept form. So we'd get -3y equals -2x minus 6. And we'd get then that y is equal to 2/3 x plus 2. Okay. So we've got this now into our slope-intercept form. That's just going to be way easier to work with. Okay, and so for the first part of this equation, or this problem, we're supposed to find the equation of a line L1, and we want L1 to be parallel to L, okay? So we want to find L1, where L1 is going to be parallel to L. So let's try this on our own for a minute or so. Try to come up with a line, L1, the equation of a line, which could be parallel to L, and try to come up with the equation of a line, L2, which is going to be perpendicular to L. Okay, let's try it on our own for a couple minutes here, and then we'll come back and regroup, okay? All right, Does anybody need a little bit more time to try these two, A and B? Please raise your hand if you want a little bit more time to work. Okay, seems like everybody's good to go. Okay, so let's start with this first one. We want to find an L1 which is going to be parallel to L. Okay, so first of all, who can tell me what should M1, the slope of L1, be? What should the slope of this first line be? Yeah, 2/3. We want it to be the same thing. We want it to be the same, right? When we're parallel lines, we want this to be the same. Okay, and now what do we think we should choose for B? Mitchell says, I did 4. Okay, not equal to 2. I did 3. Okay, great. So the point here, right, being that we can choose B to be anything that we want, because the only thing that we need for a line to be parallel would be for their slopes to be the same. So B could just be anything. Okay, so your equation should have the form y equals 2/3 x plus, I don't know, 7, or 2/3 x plus 3, or 2/3 x minus 1. Or just repeat the equation, 2/3 x plus 2. A line is parallel to itself. All right, great. Now, what should the slope M2 be of our perpendicular line? Yeah, -3/2, right? We take the negative and the reciprocal of our previous slope. Okay, and can B be just anything now again, or should it have something in particular for our B? What do we think? Yeah, Mitchell's got it. Can still be anything. Whoops. Can still be anything. Okay, so y is equal to -3/2, I don't know, plus 1. Or y equals negative, oh, sorry, that should be x, -3/2 x minus pi. Something like that. You get really quirky with it. Okay, so the point here is just that parallel and perpendicular, we're just concerned about the slope, okay? All right. Thank you, everybody, for all of your awesome participation. I like this. Okay, well, that's all we have to say about linear functions for the time being, or linear graphing the equations of lines. Okay, so now we're going to move on and switch gears and talk about functions, okay? Now, a function is going to be a little bit different than an equation, all right? A function is going to be essentially a rule, okay? So let me just, this is kind of a lot of words, so let me read it out slowly for everybody. Okay, a function from a set x to a set y is a rule that assigns to each element of x exactly one element of y. Okay? Exactly one element of y. So everything in x, we just send to some element in y. Okay? We call x the domain of our function because it's what we're going from. And the elements of y which are mapped to by f are going to be the range of f. Okay, and this just looks like a bunch of word soup, but this diagram is going to explain what we're talking about. Okay, so our function is a rule Okay, here our x is going to be all of these numbers, 1, 3, 5, 7. So if you wanted to write it out in set notation, you'd write it with these squiggly lines, and you'd write 1, 3, 5, 7 like this. Okay, and then the range is going to be everything that gets mapped to. So it's going to be the set 2, 3, and 8. Okay, and when I refer to the function itself, what I'm referring to is the fact that f sends 1 to 2, 3 to 8, 5 to 3, and 7 to 3. Okay, when I talk about the object f, I'm referring to the set of rules which define how things in the domain are sent to things in the range. Okay, so the function is the rule, the domain is the set of objects which we can input into the function, and the range is going to be the set of objects which can come out the other side of the function. Okay, so one thing that you will want to notice here is that we have something which is in our, oops, I got rid of one of my arrows here. We have something which is in Y, which is not necessarily in the range, okay? Sometimes that can happen. All right. Also, notice that we can have two things in the domain which both get mapped to the same object in the range. Okay? However, what this definition does not permit would be for one object in the domain, say 1, to go to both 2 and 1. Okay? We cannot send an object in the domain to two different objects. The reason is we say that each element of X is mapped to exactly one element of Y. Okay? So this property right here, each element of X is mapped to exactly one element of Y, says that we cannot have one going to two different places. Okay, but we can have more than one thing in the domain which wind up going to the same place. That's okay. All right, so this is the definition of a function. Okay, are there any questions about the definition before we see a little bit more examples that are going to maybe make this more concrete? Okay, I think a lot of students struggle with this definition because it's a bit abstract, but I think it will become more clear if we see it in action. So, okay, yeah, here I've got my pro tip. Multiple x values can map to the same y value, but one x value cannot map to more than one y value. So that was what I just demonstrated. Okay, so let's talk about function notation really quickly. We write f of x all the time, okay? So let me just explain what we're talking about when we write f of x. Okay, when we write f, we're talking about the function which we are applying, okay? We call this x on the inside, that's the input value. Sometimes we call it the independent variable. Okay, and when I write f of x, I'm referring to the algebraic expression of the function rule. Okay, so for example, I might have y here, which is my dependent variable, and x here, which is my independent variable. And when I write any of these three things, I'm referring to all of the others, okay? They're all equal to one another. So when I write f of x, I mean 3x minus 2, okay? And if I were to evaluate the function at a point, if I were to write f of 2, this represents the number we get when we plug in 2 for x in f of x, which, remember, f of x represents the algebraic expression of the function rule. Okay, so in our case, f of 2 would be, when we plug in 2 into 3x minus 2, we'd get 3 times 2 minus 2, which is 6 minus 2, which is 4. Okay? So this is just some fancy notation that we have for describing the process of sending numbers on a conveyor belt into like a machine, okay? Which we call the machine F or G or whatever. And we send some numbers go in, like X, and some numbers come out like Y. Okay, and it might be like 3 comes in and comes out as, or our machine sends what, 2, goes out to 4. Okay, doesn't necessarily mean that it's a doubling machine, but F just does this rule. Okay, it does 3x minus 2. Okay, the domain of our function is going to be the numbers which are permissible to send into the machine. And the range is going to be the collection of all possible things which you might see come out the other side, depending on what you put in. Okay, so these are functions. Okay, so we can evaluate functions. And evaluating functions, we just said, amounts to just plugging in. Okay, so we'll see some practice here. If we want to plug in, first of all, I recommend we always plug with parentheses. Okay, should always plug with parentheses. So here's how I would do that. F of 2, I would plug in 2 for x, and I'd square it and subtract 2. PEMDAS, this would be 4 minus 2 equals 2. Okay, B, I'm going to plug with parentheses. 3 squared minus 2. PEMDAS, 9 minus 2 equals 7. Okay, and here's the part where it suddenly becomes clear why I say we should always plug with parentheses. -3 here. -3 with parentheses, squared, minus 2. PEMDAS says I do -3 times -3. I would get 9 minus 2 is equal to 7. Okay, so in red here, common mistake. Is for people to not plug with parentheses, and they get the following. They'd get -3 squared minus 2 equals -9 minus 2 equals -11. Do not do this. Let me say, do not fall into this trap. Okay? So we always plug with parentheses. All right. So now let's do some exercises. We want to determine whether the following relationships define a function. Okay? Now remember, our rule for being a function was that we should map one input to exactly one output. And we don't really care how many outputs we have or inputs we have. We just need to make sure if a relation is going to define a function, these problems are really just verifying the fact that each x value is mapped to exactly one y value. Okay, so if we look at A here, you can see -1 getting mapped to 2, that's fine. 1 gets mapped to 3, okay, that's fine. 1 and -1 are different. 5 gets mapped to 2, seems okay so far. And this last thing suddenly becomes problematic because guess what? We've got -1 being mapped to -3. And that's incompatible with the fact that -1 is already being mapped to 2. Okay, so remember, when we have things written in this notation, what we mean here is that this is the input, output, input, output. Okay, and we said that one input can only map to one output, but we have one input which is going to 2, that's -1 goes to 2, but we also have a rule which says that -1 goes to -3. So it's like, which one is it? It's inconsistent. Right? Imagine if you had a machine and you want to use it to do something. And one time you put in -1 and out pops 2, and another time you put in -1 and out pops -3. Well, the machine would be useless because it's not reliable. Okay, it doesn't do the same thing each time you put a number in. And, if you want to, use a tool for your purposes, you really need to know what the tool does. So this is what we would call a function which is ill-defined. Okay, well, it's not a function. All right. So this is a big no for the number 1. Okay, how about this second one? Do we think this second one is going to give us a function? We've got -2, -1, 0, and 2, and these are all going to 1, -3, 2, and 1, respectively. What do we think on B? Is it going to be a function or not? Okay, Heidi says yes. Mitchell says yes. Okay, Heidi and Mitchell, let me put you on the spot for just a second and ask you the following. Is it a problem that we've got a repeated value here? I see 1 and 1 there. Okay, good, very good. Heidi's got it. No, this is not a problem. Because guess what? Repeated y values are not a problem. Okay, repeated y values are not a problem. Okay. Very good. All right, let's do this last one together. We've got y squared, so this is yes. So we've got y squared minus x squared is equal to 4. Well, if we wanted to solve for y, basically, we would get what the function is. Okay, so let's do that. I would just move x squared over to the other side. We get 4 plus x squared. Y squared equals 4 plus x squared. And if I wanted to isolate y so that I could know what the function is, I would take the square root of both sides. So I'd get y on the left-hand side. And on the right-hand side, I would get square root of 4 plus x squared. However, there's one important thing missing here, and that's that when we take the square root of a number, we actually get two numbers, both the negative and the positive square root. Okay? So in this case, plugging in x equals 1 gives y equals square root of 5 and y equals the negative square root of 5. Okay? And this is going to be a problem. Okay? Because we have one x value, which is going to more than one y value. Okay? So if we were going to write this down on a number line, we would have the following. We'd have x and y, not a number line, a table. We'd have x and y, we'd have 1 going to square root 5, and we'd also have 1 going to negative square root 5. So you would see here that we have repeated x values going to different y values. So this is not a function. Okay? So this determining whether these relations define a function really just amounts to checking that one rule. We just need to make sure that we don't have repeated x values going to different y values. Okay? Any questions about determining whether something is a function from its set of inputs and outputs? Okay, great. Then we'll move on. Okay, this is everybody's favorite part of determining whether something is a function. Vertical line tests. Okay, so the vertical line test says if a vertical line intersects the graph of a relation at more than one point, then the relation does not define a function. Okay, so here we can have some practice. If we try y equals x squared, we know that's going to look like a parabola, right? It's going to look something like this. Okay, and what we can do is we can just take our pencil here, and we're going to move it left and right, okay, across this thing, move it left and right. And we're going to look and see if at any point our function crosses the pencil at more than one point. Okay, so you can do it with a pencil, or you can just draw vertical lines, and you can see that each vertical line we draw, it's only going to intersect the graph of x squared at one single point. Okay. So that's the vertical line test. So this passes, meaning that it's a function. Okay, now we can try x equals y squared. Now x equals y squared means that we choose some y value, right? And x is going to be equal to that value squared. Okay, so in particular, this is going to be a function which is going to be symmetric about the x-axis. Okay, it's going to look something like this. Okay, it's going to be another parabola. Okay, and you can already see this is going to cause issues for us because if we take our pencil, we've got something bad happening, right? We've got intersections in more than one spot. Okay, so this is a fail. Not a function. Okay. All right. So that's how we can use the vertical line test for determining whether the graph of a relationship tells us if it's not a function. Okay. All right. So the last thing I'll talk about today will be a little bit more on domain. Okay. So so far, the examples that we've seen, we've kind of been given a domain, right? Like in these problems, they told us that the domain is going to be, for example, -1, 1, 5, and -1. Or in this case, our domain was these numbers, -2, -1, 0, and 2. Or in our very original example, we had our domain was just these values, 1, 3, 5, and 7. Okay, but oftentimes we're not going to be given our domain explicitly. What we're going to be given is actually the rule of the function. Okay, and we're going to have to infer what the domain is. Okay, so what we say is that if the domain is going to be unspecified, we just assume it to be the largest possible set of real values on which the function has a sensible output. Okay. So for example, when we define this function f of x equals 1 over x minus 2, we define the domain of this function to be all numbers which we can plug in to 1 over x minus 2 and get back something that makes sense. Okay, so in this case, our domain is going to be all real numbers except the one number that could really make this thing go crazy would be if we plugged in 2 and then the denominator would be 0. So all real numbers except x equals 2. Okay? Or you could just write x is not equal to 2. Okay, so that would be the domain of that function. Okay. All right, we'll continue with this next time. For now, if anybody has further questions, you can stay after class and speak up on the mic or type out your question in chat. Otherwise, I'll see everybody tomorrow. Yep, thank you. Have a good one.